Okay. Also want to, of course, thank the organizers for putting together what looks like a very interesting meeting. I'm sure I'm going to learn a lot. And I'm the first speaker, so I'll try to not sort of jump in too quickly. At the same time, what I'll be talking about, some of it was maybe also covered in some talks last week, and there are actually quite a few experts in the room. At the same time, I'm not going to assume that people know all the in and outs, for example, of the SYK model, which is one of the main players in my talk. It's a model that has been studied for quite more than a decade almost now, or at least about a decade. And indeed, it has very interesting relations with low-dimensional gravity and holography. But what I'll talk about, actually, the first time I talked about it, at least in the more recent period that I've been thinking about, was actually here in Brazil 2 years ago, and which is the connection between the SYK model and de Sitter gravity. Now, holography again has been extremely well developed, in particular for anti-de Sitter space. But de Sitter comes with its own puzzles. And again, I will not be able to do justice to both the de Sitter gravity aspects and the SYK model aspects. So I'll start with a little bit of a very quick bird's eye overview of things that I will not talk about, meaning just sort of introducing the players and actually some of the motivating some of the connections. So there's a bit of motivation in the beginning. And then I'll go a little bit deeper into one particular aspect of this, which indeed is the chaos correlators, which indeed will lead to a relatively simple dictionary between the two. So let me get started. The SYK model, many of you have seen it before. It's a model of just quantum mechanics. It has this n-body interaction, or p-body interaction, where, let's see if I can do this thing here. You take the Majorana oscillators and you let them interact through this random couplings. And again, I'm not going to say too much about it, but indeed it has this feature of maximal chaos, which was one of the reasons why we expected that this could be a dual to gravity. And there's a very nice sort of, again, limit of the model, which I'll mostly focus on, where you can reformulate this quantum mechanical model, which is really a unitary quantum mechanical system, which, by the way, again, I should mention, the fact that there's going to be a connection with de Sitter and a unitary quantum mechanical system, I don't know too many other examples of that. So in that respect, I think this is a really interesting sort of direction for exploration. But the realization, at least for myself, that there was this connection with gravity, and it, of course, came from the early work of Kitaev and Maldacena and Stanford and others. But especially in this double scaling limit, where n goes to infinity, but you keep this particular number, the order of the interaction p squared divided by n finite, it turns out that the theory is really extremely geometrical. And the thing to do is that you have to look at the effective interaction for the two-point function. You define a variable little g in terms of that two-point function, and then it turns out that you can essentially integrate out the fermions and write down an effective action, an exact action for this variable, which looks very familiar, at least for those who know two-dimensional conformal field theory. This thing is known as Liouville theory, and it lives on this space of functions. At least the variable g depends on two coefficients, which are the positions of the two operators. But indeed, it's a Lorentzian theory, but it turns out that this is a very interesting type of Liouville theory that already has many reasons to believe that it will be related to de Sitter gravity. And one of the reasons for it is that, as you know, in ADS CFT, you have conformal field theories with real central charge. Here you have a theory, actually, that if you compute the central charge, it's a complex central charge. And that's a hallmark also of previous proposals of connecting CFT with de Sitter space. Now, again, this double-scaled limit
again, there's a beautiful paper by the people at Weizmann, including Michael's here in the audience, where they essentially solved the model. Here I just have a few equations of sort of the essential equations that solve the model. The basic idea is that you essentially just do perturbation theory, that you take the free oscillators of your Majorana oscillators, you take the Hamiltonian, you just expand in powers of the Hamiltonian, and then because the couplings that I was writing down in the previous slide are Gaussian random variables, you can do the Gaussian integral. And then it turns out that you can formulate everything in terms of Wick contractions, which are called chords between the individual Hamiltonian insertions. And you get chord rules that count a factor of Q for every intersection between these chords. And then you have to start doing combinatorics, and it turns out that the combinatorics of doing that, and again, I could explain these equations in a bit more detail, but again, I want to get to sort of the more recent part of the story. But you can do the combinatorics, and it turns out that everything is captured in terms of what's called a Q-deformed harmonic oscillator. And then you go back to your old textbooks in quantum mechanics, essentially, and you do everything with, so the commutator here has this Q in it, where A times A dagger minus Q A dagger A, that's what the commutator is. That's the rule, and it turns out that that particular recursion relation that you can derive from the chord rules indeed can be captured in terms of these variables. Another way of deriving the same chord rule is actually to just take this action and just expand the exponential here, and then do what you're left with is a Gaussian integral, and you do the Gaussian integral, you get the chord rules. This is just introduction and summary of basically of how this model is solved, and it leads to completely explicit expressions that are going to be basically only functions of this variable little q that I introduced, which turns out to be e to the minus this number lambda. So lambda will actually play the role of a coupling constant. And in this talk, I'm going to actually consider basically the semi-classical limit of this theory. And I'm going to ask, what is the geometric semi-classical limit of this model? And I claim that the most natural interpretation of that is that it's de Sitter gravity. And one of the reasons for it is the following, is that if you do indeed DSCFT, and you do, in this case, apply it to three-dimensional de Sitter gravity, I could have written down here the three-dimensional Einstein action with a positive cosmological constant, but it turns out that you can reformulate that action in terms of a, yes?
2 times. What is the relation between the time and the 2 times?
So again, this is actually sort of a version indeed of what Bartek and collaborators started doing several years ago in low-dimensional holography, where you introduce something that you can call the kinematic space, where the so by considering this bilokal observables, you indeed sort of double the time. In the end, I'm still going to be thinking about the model also as a 1D quantum mechanics, so this time variable will play a role in what I'm going to be talking about. And indeed, it turns out that the quantum mechanics still has a single Hamiltonian, but nonetheless, at least it's a useful, how should I say, it's a correct and useful statement that this bilocal field theory can be written in this particular form. But it's true, you have to be careful in the dictionary. Another way of saying it is that if you start from the 2D perspective, the way to go back to one dimension is to look at the chiral content of the 2D theory. Yes, please indeed interrupt and ask questions, because I think that's important. Now, this theory with the complex central charge, the same Liouville theory with complex central charge, actually has indeed a close connection with 3D gravity in the same way as 2D CFT has a connection with 3D gravity. And the type of CFT that you get just by actually following your nose
and trying to derive what the boundary theory is of 3D gravity. In 3D ADS gravity, you find Liouville theory. Basically, it lives on the boundary. In the case of de Sitter gravity, and in both cases, actually, the way to derive this boundary theory, a convenient way is to do this formulation in terms of the dry bind and the spin connection. You recombine them into gauge fields, a complex gauge field in this case, and then you discover that the Einstein action looks like the action of a 3D complex Chern-Simons theory, which gauge group SL2C, which is the isometry group of the de Sitter space-time. And then indeed the boundary theory that you can associate to this Chern-Simons theory in the same way as that you get edge modes for an ordinary Chern-Simons theory. In that case, it's a Wessel-Minowitten model, and in this case, it's this complex Liouville theory with this particular central charge. And this is actually a very interesting number for the central charge because it's 13 plus or minus an imaginary number. So the total central charge of this thing is 26, which is beautiful because it means that you can treat it as a theory, as a critical theory, the same way as the world sheet of a string, where you actually couple it to a BC ghost and then basically treat this as a theory of two-dimensional gravity. This, by the way, indeed is equivalent also to then the sign dilaton gravity that Thomas and collaborators have been developing. Yes?
So why did you say it was compact? In what sense?
Non-compact.
Non-compact. Okay.
This is non-compact. In the compact case, you would just get a rational CFT. In this case, it's an irrational CFT. One of the reasons actually why this is a theory that's still hard to solve is because it's a complex non-compact gauge group. What kind of contour do you have to choose? I'll make a comment actually in a moment of how people actually can quantize this theory. And it actually happens in a rather surprising way. Are there any other questions about it? So this already connects to things that again are still being developed, the SL2C Chern-Simons, as I was mentioning, and this complex Liouville theory or the complex Liouville string that was recently also developed sort of in quite a bit of detail by Eberhard, Neumann, and Collier and Rodriguez. And indeed, so there are many results basically to make use of, that we can make use of. And it turns out that the whole thing by now has grown into a web of quite a few connections. I'll sort of briefly outline them again. And it really goes up even, it turns out, to 4 dimensions. We start in 1 dimension, which is the double-scaled SYK model. As I already mentioned, you can get this Liouville theory out of it rather directly. Although there's quite a bit to say about this connection, and then if I have time and if there are questions at the end, I can say more about it. Then this thing lives on the boundary of that 3D theory. There's also a connection here. One slightly sort of technical aspect is I mentioned SL2C Chern-Simons. That's not literally equivalent to 3D de Sitter gravity, but there's a close connection between those. This lives in 3D, and rather surprisingly, it turns out essentially through a generalization of what you might want to call the AGT correspondence, is that the exact answers that you can compute here match with objects that you can also exactly compute, surprisingly, in 4-dimensional supersymmetric gauge theory. That looks like quite a jump, but it was already known from the AGT correspondence indeed that 4-dimensional gauge theory is connected to Liouville conformal field theory, essentially through sort of it's called the 4D 2D correspondence, or the you start with the 6D 2,0 theory. I will not be able to say too much about any of these connections. Each of these arrows is a talk by itself. I will again try to indicate as clearly as possible the connection between this SYK model and the 3D de Sitter gravity, and if there are questions at the end, I can talk a little bit more about this web of connections. One last little technical point is that the SYK model has been used indeed as a model for ADS holography. I will be talking about the de Sitter space, and it's a natural question to ask, how can something be dual both to de Sitter and to anti-de Sitter?
To explain that a little bit, let me at least make sure that I try to formulate as clearly as possible what regime I'll be looking at, and in what regime people have done other kinds of studies where it connects with ADS. So it turns out that the spectrum of the Hamiltonian, since you can write it in terms of these pure deformed harmonic oscillators, you can exactly solve it. It turns out that it's basically bounded because of the Q deformation, and the energy spectrum is labeled by an angle. That's already quite an important indication. And the energy spectrum is actually finite. It runs over a finite range of the double-scaled SYK model. That's very unlike a conformal field theory, which has an unbounded energy spectrum. And the energy spectrum, again, has, the energies are labeled by this angle theta, and it's the cosine of that angle. The spectral density turns out to be basically a Gaussian, but in this case it's a periodic Gaussian, which is also known as a theta function. The fact that the spectral density is a Gaussian is precisely the harmonic oscillator Gaussian, so it's the ground state of the harmonic oscillator that in this case specifies the spectrum, because if you recall, H is actually A plus A dagger. So H is actually like the position operator of a harmonic oscillator. And its spectral density is that ground state wave function. Now, it turns out that basically the spectral density goes to 0 at the endpoints of the spectrum. And it turns out that if you take the lambda to 0 limit, which means that the Q of the Q commutator goes to 1, in that limit, if you look at energies that are in this corner, then this theory actually reduces to Schwarzschild quantum mechanics. And Schwarzschild quantum mechanics indeed is known to be dual to ADS to gravity. But that's really in this tiny little corner of this particular diagram. If I'm going to be sitting at finite values of theta, so this is theta equals, what is it? 0, this is theta equals pi, this is theta equals pi over 2. And the maximum of the spectrum sits at theta equals pi over 2. And all of the structure of the theory actually sits in this full structure of the spectrum. And the de Sitter, the pure de Sitter space will sit right in the middle at the point of maximal entropy. So it turns out, again, you can compute, and this was done in the papers indeed by the Weizmann group et al., exactly that entropy, the partition function, and you get an expression that looks like that. Again, I'm going to not write down too many of these expressions because indeed I'll be taking the classical limit, and then all of this these functions simplify, and I'm going to explain to you what the corresponding classical geometry is. But this formula, for example, is precisely the formula that matches with what's called then the Schur indices of the 4D gauge theory. But indeed, I'm not going to be going to talk much about that. I'm going to be talking about indeed the lambda to 0 limit of the SYK model, which has a known set of correlation functions, and I'm going to explain what they mean. So already in the paper of Maldacena and Stanford, they computed the 2-point function of the SYK model at finite temperature. And the answer they found looks as follows. So this is the 2-point function. O delta means that you take some power of the SYK fermions of order, what is it? Delta equals the power of the fermion divided by the number p. So the Hamiltonian has delta equals 1. Anyway, you take two of these operators and you compute the 2-point function, and it looks like a CFT 2-point function at finite temperature. Like this. So beta means that you're taking this thing at finite temperature. Now, it turns out that there's a funny kind of parameterization in the whole game. The way this thing, by the way, is computed is precisely that this thing has to satisfy the Liouville equation, because indeed the 2-point function of the SYK model is a Liouville field. This thing satisfies the Liouville equation with certain boundary conditions, and you solve that, you get this answer. Now, this answer already produces a bunch of mysteries, because it turns out that this thing is very nicely periodic, which you would have expected for a thermal correlation function.
but the periodicity is not the periodicity of the KMS periodicity of the temperature, inverse temperature. So the periodicity is off from the KMS periodicity by a factor of little v, where little v is related to the temperature in this way. Now, this is not entirely surprising, perhaps. I should have mentioned that the point that I'm most interested in, which is this point here, would have been a point with infinite temperature. So indeed, in the equations over here, that would correspond to beta equals 0, which is v equals 0. But it turns out that the function, the periodicity of the two-point function, still survives even in that limit. Now, now what you have to imagine is that you take the thermal circle, and rather than the thermal circle in terms of the real sort of Euclidean time, let's write down the thermal circle in terms of this variable phi, and this variable phi naturally has periodicity 2 pi. But the KMS periodicity is where theta with tau is periodic with beta. So the KMS periodicity is with period 2 pi times v. So that means that if you think about what you may want to call the thermal circle in the SYK model, there's actually a notion that we call the fake circle or the fake disk. If you fill in the circle, but let's call it the fake thermal circle. And only a finite segment is actually the physical circle. And these dots here are actually periodically identified. So there's actually a little circle here, green circle, which is the actual thermal circle. And then there's the fake circle, okay? Now, here I'm drawing a fake cylinder because I can complexify the time. So the phase of tau is the thermal periodicity. And then I can analytically continue to Euclidean time, sorry, to Lorentzian time, and that becomes a cylinder. And then the real part of the cylinder is these strips, and the rest sits like that. So that's the structure of the two-point function. Why does it fail? Now, it turns out that KMS is not wrong. There is the KMS periodicity, but as a function of, not every periodic function needs to be a sine function or cosine function. So what you have to do is you have to take this cosine function, you take a little segment of it, and you start repeating that. Okay, so here's the thing. So what we can do is we can analyze. So the actual right answer is just the thing that sort of is a segment of the cosine. However, it's very natural to extend, and it's possible to introduce sort of formal generators that allow you to rotate on the full fake circle. And that's the actual isometries of the theory. So this theory has an SL2 isometry group. And the isometry group of the theory acts naturally on the full circle. So the space-time isometries are acting on the full circle. Here, by the way, I drew the physical circle as a small little bit. If you go to this corner of the diagram where temperatures are low, then the whole circle is green. So the physical circle and the fake circle kind of look the same. And at that point, the dual looks like ADS. But if you go to high temperatures, this green part sort of shrinks to 0. You're left with the blue part. And I claim that the blue part is also a periodic cylinder. So both the green part, so this cylinder actually splits up into 2 cylinders. This thing is going to be dual to the ADS2. And this thing is going to be dual to the S3. That's my proposal. And I think I'm going to give you evidence for that. It turns out that what happens is that the place where the jump happens is where the two coordinates are on top of each other.
So the cosine, at least it's a periodic, it's a 1 over cosine. So it does this thing, and then at the 0 of the cosine, it will go to infinity. But it turns out that the 2-point function cannot get bigger than 1. So that's why the 1 over cosine has to be truncated at the point where the 1 over cosine is equal to 1. No, actually, it turns out that in the BTC black hole you have similar issues. So indeed, the KMS periodicity of the BTC black hole has sort of similar kind
I'll ask you more later. Thanks.
yeah, and there were papers by Fitzpatrick et al. That sort of discussed this thing. You're right. Yeah. So anyway, so if you look at the 2-point function, you already sort of discovered the structure. Yeah, it's basically if you take the identity character dominant, the 2-point function that follows from the identity character, you have the exact same issue appearing there in that context. Well, not in Euclidean time, but in the phi circle.
Sorry, may I also ask a question? So why do you get this different dimensionality? I mean, you know, on the left-hand side, the green and the blue has the same number of space-time dimensions, and on the other side, you have.
It's not a tensor product. I'm just saying this is it's it's not a tensor product here. I'm not taking the product of these two. Okay. I'm either sitting here or I'm sitting there.
Okay, but still, how can they have different dimension if on the other side everything seems to have the same dimension?
What do you mean by dimension?
I mean, this is ADS2 and that's d zeta 3, so
there's a Q here.
Right, okay. So that
I could call this thing Q ds2 as well. But it turns out that Q ds2 is really, you have to think about it as 3D as coming from the 3D theory. Okay. Okay, so now I'm going to look at the OTOC. The OTOC was an important part of the motivation. Yes. Oh, sorry.
Not the disjoint in analytic sense. So what do you exactly mean by this disjoint?
Now, what I mean is that these points, these endpoints are identified. So if the value of a function is the same in those endpoints, then I can periodically extend that function here and then have a thing that lives on the green circle.
But doesn't the isometry of the generator get acted?
Yeah, so the isometries actually indeed will not act on this space. The isometries will basically only act on the extended space.
Oh, okay, sure.
One thing that's already going to be extremely suggestive is that, I'm not sure if I actually have a slide for this, if I consider a massive point particle in 3D de Sitter space, it creates a conical deficit. To me, this thing here is a conical deficit. That's literally what it is. Because what it looks like is that I have an isometry group that wants to have 2 pi as my periodicity. But if I live on the blue cylinder, my periodicity is not 2 pi. It's 2 pi times 1 minus v. And that's going to be my periodicity if I live on the blue cylinder. So the blue cylinder, when v is non-zero, has a conical, has sort of in the interior of it a conical deficit relative to this one. And it turns out that that conical deficit is precisely very naturally present in de Sitter gravity, because in de Sitter gravity, if you put a point particle somewhere, it creates an angle, a deficit angle. By the way, that's not true in ADS gravity. If you put a heavy point particle in ADS gravity, if the particle gets really heavy, you're creating a BTZ black hole, and that thing has no longer an angular deficit, but it has a boost deficit, basically. Okay, so now I'm going to start with a calculation that was actually done by Chi and Streicher maybe 6-7 years ago, where they computed the OTOC in SYK, And they've done the calculation in a way, and I only discovered this, say, less than a year ago, in a way that's very natural from the point of view of actually interpreting it in terms of 3D gravity. And I'll explain how the computation was done. So if you want to compute the OTOC, it's a 4-point function. Typically, you take two operators identical, and then you look at the 4-point function, where you compare different orderings. Now, the way Streicher and Chi started, and the way Streicher actually computed the OTOC at arbitrary temperature, indeed, is to consider first what they call an auxiliary object, but this object turns out to be very natural, actually, even from the holographic point of view, where they exponentiated the 2-point function of one of them, like that, and then they considered the 2-point function of another 2-point function in the background of that exponentiated operator. Now, if you think about it a little bit, this exponentiated operator by itself is actually a 2-point function of a field with conformal dimension L, little l, or the squarely L. So you can really think about this thing as a 2-point function. The reason why that thing is actually just a 2-point function is because I explained that psi is the variable little g. This thing is therefore actually, in terms of the variable little g, just one of the exponential operators. So it's an e to the power g. So it's indeed actually a 2-point function. This object here by itself. And then the whole object is a 4-point function. Now I'm thinking about the thing on the right as creating a background for the second propagator. So it's called a twisted 2-point function for tau 1 and tau 2. Because of the presence of these two other operators. And because of this thing is just being quadratic in the fermions, you can actually easily compute this correlator again. And essentially what you have to do, and this is how Streicher indeed computed it, is you solve the Liouville equation, because this 2-point function solves the Liouville equation. But you only have to make sure that you impose an appropriate jump condition when this thing goes over this other object. And that jump condition is like a deficit angle, turns out. So he solves the Liouville equation with a certain jump condition. And that's how he actually computes the OTOC. And the answer that he finds looks like this. So indeed, there are going to be different regimes. Phi is again this fake circle angle coordinate. And depending on the ordering, you either get the 2-point function that Maldacena and Stanford already had computed. That would be the TOC, the time-ordered 4-point function. The OTOC turns out to look like this. This is what he found. So that's the answer. It turns out that this is an exact answer. Indeed, in this, basically, I call it the WKB limit of the double-scaled SYK, where you take the lambda to 0, but you keep your energies all so that you still have finite back reaction. And I'm going to give you an interpretation of this OTOC from the sitter point of view. X is, oh, I had it on the previous slide probably. I hope I had it on the previous slide, but maybe not. Maybe it dropped off. Maybe it dropped off. It's pi v over 2. Yeah, but it's just because I didn't want to write all those pi v's over 2. Okay. So now I'm going to interpret this thing from the sitter point of view. And the basic idea is indeed, as I mentioned, is that one of the 2-point functions, the sort of the red one, which is the background. So this is the way exactly in which at Hooft already long ago started computing OTOCs basically in gravity by considering the propagator of a light particle in the background of a heavy particle. You include the back reaction of the heavy particle, and you look at the propagator of the light particle. And now we're going to go into 3D de Sitter gravity. And if I have a heavy particle, it will create a conical deficit along its world line. And that deficit is proportional to the mass of the particle times g Newton. And then basically the idea is that if you look locally in the zeta space just looks like the zeta space, but then if you have matter somewhere and you go around a matter source, you come back up to an isometry. In this case, the isometry is just a rotation. So it will look like that. Okay, so this is how you specify in the zeta gravity what a matter particle does. And then what you have to do basically, let me still go back, is you take the 2-point function of this other light particle in the background where this monodromy actually acts. Yes.
I'm supposed to, I mean, this is just, I'm supposed to think about the two-dimensional space embedded in the zeta 3, or it's just the fall?
This is of course a Penrose diagram, which Penrose diagrams are always two-dimensional. But indeed, if this is the zeta 3, then this should be a two-sphere. The future should be a two-sphere, and that vertical is time. So the vertical is the time coordinate, and this is an S2, and the future is an S2. That's
how is that related to the
I'll explain on the next slides. Is there another question? So let me do that now. So indeed, so now I have to compute the propagator in the background of this particular this matter source. Three-dimensional zeta. You can conveniently write it in terms of a 2x2 matrix with determinant equal to -1. Then in terms of the embedding coordinates, right? So x are the embedding coordinates, and this equation then becomes the zeta embedding equation. You can solve that equation by the usual global coordinates if you want. And isometries in this embedding language just act like this. I take a matrix in SL2C and I conjugate the matrix like that. Geodesic distances are just inner products between the embedding coordinates. At least the cosh of the geodesic distance is that inner product. Now, I'm going to be interested in 2-point functions between scri plus and scri minus. And if I go to scri plus and scri minus, then basically I go to past and future infinity, and then up to an overall prefactor. This matrix S is as X becomes another matrix Z, but that matrix Z now has determinant equal to 0. So points on scri plus and scri minus are parameterized by a determinant, the matrix of determinant equal to 0. And therefore, I can take that matrix and write it as a tensor product like so. And basically, that matrix on scri plus, the points on scri plus and scri minus are parameterized by a complex number Z. And basically, this tau variable is just basically the polar coordinate, and the phi coordinate is the azimuthal coordinate, okay, the phase. Now, the propagator between the future and past infinity can be expressed in terms of the geodesic distance between the two things. So let's compute indeed the dot product between the points at infinity, and it factorizes into a product where this wedge is an epsilon symbol that contracts these two component objects. So this is like a twistor parameterization, if you wish, of scri plus and scri minus. And then if I normally just in a regular CFD, by the way, the same computation you can do in ADS. If I take the 2-point function, the 2-point function looks like that on the boundary, and it factorizes into two-point functions for these two component objects. So this is the 2-point function without back reaction, but now I'm going to do the back reaction. So I introduce now my source particle, and I'm going to have a 2-point function where the green wiggly line will now fill the monodromy of the heavy particle. So the only thing I have to do is to actually transform the location of the one point relative to the other. So this is the shock wave, if you wish. And that shock wave, it goes by conjugation on the embedding coordinates but it just goes in the fundamental representation in terms of this two-component object. Now, at this point, I can just compute this object. For given positions on scri plus and scri minus, and for given rotation matrix, I get this answer. This answer already looks very much like the thing that Streicher wrote down. Turns out that this is a special case of Streicher's two-point function, a twisted two-point function. And indeed, what you find in this case is that in that particular kinematic configuration, that the OTOC, which is the thing that actually I compute here in the Sitter space, is just the square of the OTOC in SYK. And so the SYK basically lives on the tau space. So I take the time of SYK, I complexify it. That complexified time parameterizes this two-component vector, and it parameterizes point on scri plus, and the other one parameterizes a point on scri minus, and then this is the relationship. Yes.
I mean, it's a 4-point function, but why is this related to reverse time ordering in any quantum mechanics?
Yeah, I can say a little bit more about this. Actually, indeed, Vladi did a computation where he's sort of computing something that looks more like an OTOC. Yeah. I'm calling it the OTOC in the following sense. Rather essentially, indeed, in computing the OTOC, you have to decompose sort of your parameter space, your configuration space into different regimes. And I was emphasizing that there's indeed a transition function if you start interchanging the two things. As you know very well, that transition function in double-scaled SYK is characterized by an R matrix. And the R matrix is really, from the 3D perspective, it's also a version of the braid matrix. So the R matrix and the braid matrix are directly related. It's clear that here in this case I'm looking at a braided, maybe I should call this thing a braided two-point function, but it has the same presence of the same R matrix that appears in the OTOC in the SYK model. Yes.
I'm confused by the i's in the formula because I would have thought if it was a two-point function that I could understand as living at the future of de Sitter 3, it would be manifestly real because operators at baselike separations commute.
Right. The only reason that it takes me long to write this paper is because of those factors of I and Z asymmetries. So there are different conventions you can take. You can either first work in Euclidean, go to real time. So I have two sets of calculations where we do things in Lorentzian and where we do things in Euclidean. And I'll be honest. So it turns out in Streicher, so which factors of I are you talking about? This, for example? Or?
Any of them for the moment. My question is just if I think of this correlator as living at the future infinity of the real de Sitter 3,
correct,
with the usual Lorentz signature, correct. In that context, is the correlator real or is it not?
It turns out that this object is not real. This object, of course, is.
Okay, but is the thing you've written as phi sub m, is that real?
Yeah, it's also the product of the, so this is times the complex conjugate.
Okay, great.
So it indeed becomes sort of complex only after sort of factorizing it into the two things. But indeed, there are funny factors of I. It turns out that if you take an SYK operator with a real conformal dimension, then this factor of I is not there. The reason I want to put the factor of I there, it turns out that if you look at the at the de Sitter back reaction, the real conformal dimension in SYK corresponds to a particle with mass below the threshold. So there's a funny separation between light particles and heavy particles in SYK. You either have sort of a, what is it called, the two SL2R types of SL2R representations. If you want to have a heavy particle, you want to have a particle with a complex conformal dimension. Now, that seems a little bit suspicious because SYK doesn't seem to have things with complex conformal dimension. However, precisely the definition that Streicher took for his two-point function namely this one here, actually Streicher had a factor of I in that exponent. And he was interested in real scaling dimensions. The only thing that I would need to do in order to go from a particle with heavy mass and light mass, where there's a factor of I that goes into the representation label of SL2R, is to change the L in that exponent. So that's still a physics question to ask, is does SYK naturally have observables where I can write this bilocal expression with or without a factor of I. So factors of I are important. But for the rest, I think, yeah, it's the other factors of I are naturally related to being either in Euclidean or in Lorentzian signature. Are there other questions? Okay, so I don't have that much time. I can very quickly flash a few formulas that generalize this thing, because it turns out that this is a special kinematic configuration. So this, by the way, is the summary. So this tau variable, the complex time of the SYK model, parameterizes a point on Scri plus. In terms of polar coordinates, this is the dictionary, and then you have this particular relationship. Let me make one other comment, which is something I've not talked about. 2 years ago, with Vladi Narvansky, we wrote a paper where we actually computed a two-point function, a rather special type of two-point function, also in a product of two SYK models, where we basically took a convolution product between the operators in one model times the other, in such a way that the operator actually commuted with them the sum of the two Hamiltonians. We computed the two-point function, and we found that the two-point function exactly matches with the Green's function in 3D de Sitter. But that two-point function was living on a world line in the book. So the question is, how do I go from Scri into the book? Now, it turns out that there's a very natural way of doing that. So what you do is that the operator, so I can place a point now at a point X in the book, an operator there, by essentially doing a version of HKLL. It turns out that the HKLL prescription rather naturally turns into the following formula, where you think about this O as living in a particular representation of SL2, where G acts on O of tau by C tau plus D O of A tau plus B C tau plus D, where the matrix ABCD is an SL2 matrix to the power delta, I guess here. So operators are naturally representations of SL2, and then you can take matrix elements by integrating them against each other. And it turns out that if you take this operator, and again you work in this limit that I've been the lambda to 0 limit, and compute endpoint functions of this thing, you actually find endpoint functions of free fields in 3D de Sitter. It's an identity of hypergeometric functions that this thing can be decomposed in this particular way. So it's possible to generalize this dictionary and already do HKLL, where you also put things in the bulk. And then indeed the time coordinate will be labeled by this element here. So the time coordinate in the bulk will be labeled by these A, B, C, D coefficients. So that's the thing that one can do. Here, by the way, there's some other formulas that you can develop, which indeed create a more precise match with the Streicher formula. Maybe I'll skip those. This is a long list of things that I have not talked about. And since there's still 10 minutes, maybe what I'm going to do is I'm going to stop. We went to the restaurant yesterday and we got a menu. This is your menu. And you can ask a question about any of these topics, and I will be able to give you at least some form of an answer.
All right, thanks, Herman, for this very clear talk. So please choose from the menu. So, Jan. Yeah. There's a microphone. Wait, maybe.
Maybe this is a question about the second bullet point. So your relationship is a bit like, the fact that the sitter is OTOG squared in SYK. In ADS is kind of the statement about conformal blocks in the theory being the square of, also the correlators in the 3D gravity theory being the square of conformal blocks. Now that's an operational procedure that relates certain computations, and that tells you that the Hilbert space of the Chern-Simons theory is the space of conformal blocks and so on. But if we interpret the Chern-Simons theory as a theory of 3D gravity, that's not the Hilbert space we are interested in, because the Cardi density of states that you derive from the black hole partition function is not the actual density of states of the space of conformal blocks. It's a different interpretation of this, of the computation. So what's the analog? What are the computations here that would give you like the analog of the Cardi density of states? And are we supposed to think about the Hilbert space of the sitter 3 in terms of the space of conformal blocks, or is there a different sort of Hilbert space somewhere in the background? And what's the relation of that to the SYK Hilbert space?
Okay, very good question. So indeed, one reason, obviously this can be exciting only indeed if this question has a more precise answer. It's fair to say that DS holography in the sitter space is difficult precisely because of this issue. And I think the slide that I had over here is probably still the relevant one to, let's go back, here, to talk about. Because again, there are different ways of thinking about Hilbert spaces. This actually, although it suggestively corresponds to this fake circle, but it's actually also the static patch in the sitter space, this green thing. So the world line here could be the space on which we want to sort of to which we want to associate a Hilbert space, and that was indeed the philosophy that I took in the paper with Narevlansky. And at that point, we sort of said, okay, well, maybe, for example, if we think about entropy and things like that, we should be thinking about entropy of the static patch. It indeed turns out that the 2-point functions of these things indeed satisfy the actual KMS condition of the, I should have mentioned, the fake temperature is really the de Sitter temperature. So from the point of view of the holography, the fake temperature of SYK kind of is as real as the de Sitter temperature is. So that's really the temperature of the environment. In the paper with Radi, we identified the Hilbert space of the system, really with the Hilbert space of 2 SYK models, but where we required that the sum of the 2 Hamiltonians vanishes. I think that's still probably a good prescription. So essentially, the Hilbert space of the SYK model is still associated with the Hilbert space of the static patch of an observer in a particular static patch. Now, you're talking about DSCFT, and indeed one of the weaknesses of DSCFT is precisely that the CFT lives on Scri plus and Scri minus, and it seems as if what I was doing was placing the SYK model on Scri plus and Scri minus. But actually the way we discovered that particular prescription is to start actually from this one, where actually the holography takes place on the world line. Then you discover that the system still has actually isometries, because obviously I can move this thing around, this point X. If I just take this dictionary, which maps Hilbert spaces to Hilbert spaces, and I now send this point X to Scri plus and Scri minus, I get that prescription. So rather than starting with that and going with HKLL back into the bulk, it's better to start here and then take the boundary limit. But the dictionary is simpler on the boundary for the same reason as that it's simpler in ADS-CFT. But the Hilbert space indeed is associated with the time evolution in the bulk. That would be at the moment
my most accurate answer.
Okay, there was another question over there.
In one of your first slides, you introduced the Q commutators. Is there any special things happening when Q is a root of unity? And do you have some possibility to relate your construction to representation of quantum groups directly in operatorial formalism?
Yeah, that was a very good question. So it turns out that the Q is a number between 0 and 1, which is not possible to do that, I think, for a compact group. So it's a hallmark of having a complex group. And in particular, it actually corresponds precisely to this thing that it has a complex central charge, and actually precisely that the if one would follow the same procedure of deriving the quantum group structure, and actually I have a bunch of slides that I'm not showing that do this more explicitly. Indeed, there's a way of going from SL2 of Chern-Simons theory, say SU2 Chern-Simons theory, to a quantum group, in which case indeed Q can be a root of unity. But if you do it for SL2, you can get Q either a continuous variable on a circle or on the real line. And in this case, Q sits between 0 and 1.
Sorry, I have also another question, because you mentioned the connection with the Liouville theory. And, but in your model, you have already some fermionic degrees of freedom, which are the Majorana field. Would you expect that it is possible to generalize, even if supersymmetry and de Sitter don't go well together, but to have some supersymmetric generalization already with the data that you have, some super Liouville?
People indeed are currently constructing what you can call the supersymmetric complex Liouville theory. So indeed that development is happening, I think. But it's an interesting question, because indeed there's obviously some tension between supersymmetry and the Sitter space. But I would only sort of at the moment know how to maybe get started with this on the Liouville side. I wouldn't necessarily know how to start with this from the gravity side.
Okay, great. Are there, yeah, please.
So you talked about de Sitter being associated with the fake disk at some level, and you talked about the fake disk arising from taking this two-point function, which is not in fact analytic if we make the tau circle have the KMS period and doing an analytic continuation. So if I understand correctly, the non-analyticity is allowed because you've taken a double-scaled limit. If you were at finite n and SYK, you'd have something analytic and so forth. So my question is, do you have some idea of how this kind of correspondence with de Sitter might persist at a level which is not the strict large n limit, where that non-analyticity would disappear?
Yeah, let me make maybe another comment about this. It turns out that if, for example, okay, in the double scaling limit, so there are two ways of relaxing limit. For me, because actually I think with holography, the first order question is typically the classical correspondence. If you don't understand the classical correspondence, you don't understand the dictionary. So this is why I was focusing on classical. Then you can go quantum by making this Q parameter finite. What's remarkable about the double-scaled SYK model is that it's still an exactly soluble theory. Everything can be computed, and it's also exactly equivalent. At least there's an exact dictionary between correlation functions in double-scaled SYK and certain things, correlators you can compute in SL2C Chern-Simons. And I think this SL2C Chern-Simons, you can probably lift them also to objects you can compute in 3D de Sitter gravity. But then if you take n finite, then yeah, things are much less well controlled. I should emphasize that, for example, Lenny Susskind, he really wants to think about sort of the large but finite n case, and he wants to basically go to energies that are of order 1 over n. And then there are no controlled approximations,
And then actually, to be honest, the evidence that there's a gravity dual in that regime is not very strong. So I would say the corrections in terms of p squared over n are completely understood in terms of gravity. 1 over n corrections are not. And I think maybe what you're talking about would require 1 over n.
Yeah. And just as a step towards that, but still taking...
Sorry, let me still make one other comment. Sure. It turns out that the isometry group, the de Sitter isometry group, does get Q deformed at finite Q, so at finite p squared over n. The isometry group is no longer a group, it becomes a quantum group. And to what extent is a quantum group actually a symmetry group? That's a bit hard to actually make precise. So you can only see the classical correspondence in the Q to 1 limit. And you have to work with quantum groups if you work at finite Q.
And just as a step kind of in that direction, but still sticking strictly classical, is there a story about de Sitter 3 where future infinity is not a sphere? Because in principle, you could use any two-manifold.
Not so easily. It turns out that even, for example, the equivalence between people, there's the complex Liouville you can put on any Riemann surface. The sine JT or the Q sine JT theory, I think you can only put it on things with Euler character 0.
0.
Euler, so Euler character.
So not spheres, but only tori.
Not spheres. So you need punctures, or you need holes. So indeed, there are certain things that only work for certain topologies. It turns out that actually one of the very nice things about this corresponds with the n equals 4 Yang-Mills theory, n equals 2, Yang-Mills theory. So it turns out that the SYK correlators functions are equal to things that are called half-Schur indices of pure Seiberg-Witten theory. And then pure Seiberg-Witten theory, Seiberg-Witten famously introduced the Seiberg-Witten curve. Gaiotto explained the Seiberg-Witten curve by compactifying the 62,0 theory on a sphere. But the sphere had 2 punctures. So it turns out that the natural geometry associated with double-scaled SYK is the Seiberg-Witten curve of SU2 Seiberg-Witten theory. It's the sphere with 2 punctures, and the way I would like to interpret it is that the 2 punctures are the north and the south pole, where basically the conical deficits sort of sit. So it's like the natural place where you have a Schwarzschild de Sitter geometry. So there's a nice correspondence indeed with that.
Okay, before we pause for coffee, let me ask one quick final question. So you showed very nicely that the ADS dual sits at the corner of the spectrum. And so can you deform continuously from ADS to DSS by increasing the energy?
No. So I had this variable theta, which is some angular variable that goes between 0 and pi. In order to go to ADS, what you naturally do is you write this thing as lambda times S.
Okay.
And then you take the lambda to 0 limit with S finite. That's how you get Schwarzschild, ordinary JT gravity.
So sorry, what is S?
Defined by this equation.
Okay.
Whereas what I've been doing, I've been taking the lambda to 0 with theta finite. So it turns out that S is naturally identified with the energy, the square root of the energy in JT gravity. So this S is like square root of the JT gravity energy.
Yeah. Okay.
But basically, you have to take the energy of order 1 over lambda and then take the lambda to 0 limit.
Okay.
And then you have a whole new geometry basically that comes from that. And that geometry is what I've been talking about.
Thanks a lot. Okay, I think in view of the time, we should probably stop here and thank Herman again for his beautiful talk.